Programming Throwdown, episode 86, Wolfram Language with Stephen Wolfram. Take it away, Jason.
Hey everyone, Happy New Year. Welcome back. And we are starting the year off with an amazing interview. Very rarely do we get the opportunity to interview someone who actually invented a language. Every show we always talk about a language. And here we have Stephen Wolfram on the show. And Stephen, why don't you kind of describe yourself and Wolfram Research and kind of walk us through your journey?
Oh boy. Okay. This is a describe yourself in a few words. I remember I could tell you some interesting stories about times when people have said that to me. But
all right. Well, we have an hour, so you have plenty of words.
Well, let's see. For the last 32 years, I've been working on what's now Wolfram Language. And a couple of things that many people will know about have come out of that. One is Mathematica, which was first released in 1988, so we just had our 30th anniversary. And the other is Wolfram Alpha, which came out in 2009. Those are Wolfram Language is kind of the core of those things. I kind of started working. Well, gosh, let's see. What's the story? Well, I got really interested in physics when I was about 10 or 11 years old, which is a depressingly long time ago now. That's beginning of the 1970s. And one of the things about doing physics is you have to calculate all kinds of things with math and so on. And I was very enthusiastic about physics and very unenthusiastic about calculating things with math and so on. And so I kind of I said, this is really boring and very mechanical and should be able to be automated. And that time was about 1972, 1973. I first got exposed to a computer, which was a big thing the size of a large desk and so on, programmed with paper tape and all those terrible things. Mm-hmm. But I started trying to figure out how to essentially automate the computations that I might want to do for things like physics. And that worked really well, and I discovered all kinds of interesting things in physics. And I got my PhD when I was 20 at Caltech. And then I kind of, at that moment, actually, I was like, okay, I've been using all these computer tools, and I've kind of outgrown the ones that exist today. If I want to do all sorts of science and things that I'm interested in, I'm going to have to basically build my own tools. So I started building.
So can you dive into that thought process a little bit? So how did you decide that you had sort of outgrown the tool, right? I mean, people are talking about, let's say, Turing complete and all that stuff, right?
I'm sorry.
I was just going to say, you could say, you could do anything in assembly language, you could do anything in C. So it requires, I think, a lot of to some degree experience, or maybe wisdom is the right word, but to recognize that the productivity hit you would take from having to build some tool from scratch is justified by the gain you would get once you have that tool, right?
Yeah, it's been interesting in my life. I spent for example, a decade doing big basic science projects starting in 1991. It was after the first version of Mathematica came out. And I realized that, a decade is a long time. And, but then I realized that actually, if I had not developed Mathematica first and then done that science, it would have taken me 30 years to do what I managed to do in 10 years. So the 5 years before that I spent developing Mathematica as a tool was, in the end, I was coming out way ahead relative to saying I'll just cobble together what I need to be able to do the things that I want to do. But back in 1979, the story was in a sense simpler, because I had been so the idea of sort of doing mathematical and algebraic computation by computer was one that had originated in the 1960s. People had built a variety of kind of research systems for doing that, and I had used kind of most of the ones that were at all practical. For some strange reason, other people never used them. It was like there were all these physicists and they were spending all their time with pencil and paper and so on, calculating things, and it was like, no, I can just use a computer to do that.
So at that time you're talking like Fortran, mainly Fortran, right?
Well, at that time most theoretical physicists did not use computers.
Okay.
Most, I mean, what happened was if you needed a computation done, you would find some programmer who would go off and do the computation. And in terms of programming languages, yeah, Fortran was the main one. It's still Fortran 66.
Hmm.
And if you were a real programmer, you used assembly language. And I remember people telling me, oh, even in the 80s, people telling me, oh, all these high level languages like C, they're never going to catch on. If you want to do something serious, it has to be assembly language.
Yep.
Um,
Yep.
that's kind of a story that will repeat because in terms of Wolfram language, it's kind of a higher level language than one seen elsewhere. And people still say, oh, if you want to do something serious, you have to use some lower level language. It isn't true. And the course of history, I'm very confident in the course of history in terms of that.
Yeah, I mean,
But
if you're
back
willing to play the long game, Moore's law always works in your favor, and eventually, almost any of these optimizations that you get from C end up not being that important. So, for example,
but I
if
don't
yeah,
think that's the point. I think that the real point is it's sort of the conceptual level that you can reach. I mean, we're jumping around a lot, and I mean, this is super interesting stuff. But if you want to go back to the narrative of how I came to start
no, jumping around is fine. Yeah, let's talk
uh,
about the trade-offs between, say, Mathematica and writing it in C. I think that's interesting.
well, okay. So first thing you have to understand is in terms of Wolfram language, how do I view that? What do I think of it as? I view it as a computational language, a little different from a programming language. It's a super productive programming language, but more importantly, it's a computational language. It's a language for communicating computational ideas in an explicit, concrete form. And it's a language that allows computational ideas to be communicated and understood both by people and by machines. So kind of my goal in Wolfram language is to do something really very different from the goal of other kind of the traditional programming languages. The traditional programming languages, it's kind of, okay, I've got my computer in front of me. I need to tell it, how to operate its transistors, so to speak, in the best possible way to get, to get what I want done.
Hmm.
What I'm more interested in is how do I represent in a language the way that I think about something computationally, and then it's the job of us as the implementers of the language to get the computer to take sort of the goals that humans have expressed and get them implemented as efficiently as possible. Now, in terms of and what we've tried to do in Wolfram language is to build as much knowledge as possible into the language. So typical language, there's a fairly small core language, and then maybe people add libraries and all kinds of other things to it. But in Wolfram language, the idea is have as much as possible built in a coherent way into the language, and that's a lot of work. I mean, the last 32 years, basically, I've spent a large fraction of my time trying to fill in and just build lots of stuff coherently into the language. I mean, pretty much, every day I'm working on kind of the design of the language. In fact, for the last almost a year now, I've been doing actually live streaming a bunch of our internal design review meetings. I think we just passed 250 hours of live stream design review meetings.
So that's to the public, so anyone can just
To the
watch that.
public. Yeah, absolutely. It's on Twitch and Facebook Live and YouTube Live.
Wow, that's
And
awesome.
it's really pretty interesting dynamic. I mean, there's some pretty interesting, sophisticated people who tune in and they give some great comments. And I think we've done better design as a result of things people have suggested. I mean, it's always interesting because, today, let's see, I did one today. Probably the one yesterday I did a couple yesterday actually. One yesterday was interesting. Was about this relates to the whole thing about the language knows stuff. So one of the things it knows is it knows geographic data about the world. So it knows the locations of all the cities, the populations of all the cities. We happen to have curated the borders of all historical countries that are known. So there's a few thousand historical countries from the Roman Empire to the different gyrations of different countries and so on. And so we got all that data, and the issue is how you deal with the language design of talking about a historical country. So we were starting off looking at I I was like, let's look at the Roman Empire in 55 BC. And then one of the guys who's worked on this stuff said, well, actually, the Roman Empire didn't exist in 55 BC. It was the Roman Republic in 55 BC. And it's like, okay, what does it mean for the entity? What counts as France, for example?
Right.
It's changed its name at various times. And so, so these are questions that are an interesting mixture of sort of real world issues and kind of precise language design. But more than that, this was actually mostly about how do you think about the sort of time series character of country borders, given that one only knows them every year, and how does one deal with the fact that one has a time series which kind of holds to one side but not to the other, et cetera, et cetera, et cetera. But this is kind of the story of my life is trying to figure out how to take these kinds of thove and make a precise symbolic language in which one can talk about, let's say, historical countries, or today's live stream thing happened to be about the display of data sets and figuring out how to parameterize the way that a hierarchical data set is displayed and elided, and so on.
So one thing that has always interested me is this idea of sort of push versus pull when it comes to data. So, for example, if we take, let's say, Google's web mirror, like Google's indexer, right? They crawl the web, they gather a bunch of data, but the websites themselves are not particularly participating. They're sort of involuntarily participating.
Yeah, I mean, what we've done is very different. I mean, what we've been interested in for the last, 20 years or so is collecting and curating as much data as possible about the world. And so, what we've done mostly is, we work with sort of the primary providers of data, or we collect it ourselves, and we try and make as good as possible a kind of a computable version of the world. I mean, there's a big difference between, data that's good enough for somebody to read it on a web page and data that's good enough to compute from.
Mm-hmm.
And that's you could say, well, if you can do some, NLP extraction of stuff and you can get it 80% right, and that's fine, so long as you got a human to see that 20% of it is totally ridiculous.
Right. Right.
If you're going to, in fact, one use case that we've been much involved with in computational contracts and smart contracts on blockchains and things like this, in the end, if you want those to allow one to sort of run the world by machine-to-machine sort of contract interactions, you have to have some source of facts about the world. You're selling weather insurance. You want to know, did it actually rain yesterday in wherever?
Right.
So, in fact, right now, the source in the world, for better or worse, of computational facts is the Wolfram Alpha API, because we've collected and made computable basically a huge range of kinds of facts in a way where those facts can actually be used as inputs to computation in a consistent fashion.
Oh, I've heard about this where there's a I think it's a betting site where you can bet on facts. You could bet whether it's going to rain tomorrow, and it's all done on blockchain.
Yeah. I mean, that particular activity egregiously violates our terms of service.
Oh, okay. All right.
Nevertheless, people do it all the time.
Okay.
We hope to, one of the issues is, it's like, who's liable if we say so-and-so won the election in Bolivia or something, and, we do our best to get it right, but it turns out, a lot of people bet on it one way and goes the other way. It's like, how does this work?
Oh, that makes sense.
I think what's emerging is whatever Wolfram Alpha says is true, which puts us in a curious position, and we're sort of working to make our sort of computational fact infrastructure, which deal with these kind of deciding things at that moment, so to speak, in as robust and a way as possible. But I think we do. We've gotten to much of the computational fact, computable knowledge that we deal with is knowledge that wasn't stuff that happened today. I mean, we do deal with plenty that happens today, earthquakes, flight
Sure.
times, all this kind of stuff. But I would say the majority of stuff people are using right now is sort of facts that might be, properties of a chemical, or, box office results from a movie or something like this. Things which are, firmly in the past, so to speak, rather than things that, just happened and are complicated to verify.
What about, there were things like OpenPsych, for example, where people could specify, a list of facts about the world. Is there any way to sort of scale this outwards so that anyone can contribute, and some way to deal with, Byzantine contributions and things like? Have you thought about things like that?
Of course we have, yeah. Of course, we've had a whole program of volunteer data curators and so on. It hasn't been particularly successful.
Mm-hmm.
I would say that there are particular well-collimated types of data where people have been very good at contributing and been very helpful to us. Like, for example, properties of fictional characters in books. That was done by a big volunteer effort.
Okay.
But I would say in more precise kinds of data, usually there's some sort of professional data collection operation that's doing it, or nobody has done it. But to do it consistently is non-trivial. I mean, what we found is, we employ lots of data curators, and we found that's more efficient than, having volunteers do it, because it's just, we can train them. They use a bunch of nice tools, which we could make available to people, but, it takes some training to get to be a good, efficient data curator. It's not everybody's cup of tea.
That makes sense. I think there's also great ambiguity in the structure of almost any data. And so if you just give it to this heterogeneous group of volunteers, you're very rarely going to get a consistent structure.
Yeah, I think one of the challenges of data curation, and a thing I hadn't really realized, but we've built this whole sort of culture of doing data curation, and I hadn't really realized how unique that is. Because we do a bunch of work with, all sorts of world's sort of largest companies making basically private versions of Wolfram Alpha. So the Wolfram Alpha that people know that powers Siri and also has just started powering Alexa is that's working on public data. But we've also had a sort of growing business on making enterprise versions of Wolfram Alpha, where we're taking the internal data of some large company and letting people ask unstructured questions about that internal data, making use of public data plus their internal data. So, somebody might say, what were my sales between Christmas and New Year in sub-Saharan Africa or something? And, for that, you have to know things about the world, like Christmas and New Year. You have to know, what's sub-Saharan Africa. You have to be able to know currency conversion rates, all those kinds of things. And to answer that question, you have to go be hooked up to the, internal databases of company X to go and answer that. So we've been we've done a bunch of those things, and one of the things that's been interesting is that people are sort of horrified. You mean you actually have to go and do things with humans to make all this stuff work? Well, yes. I mean, we have very good, we've got very leading edge machine learning stuff and NLP stuff and so on. But that's not, if you really want to make computable data, you can't use that stuff. You can use it to help prime various pumps, but in the end, humans and experts end up having to be in the loop if you actually want to build something that is capable of being a foundation on which you can build sort of a big computational tower. And I think one of the things about the culture of data curation is it's interesting because there's a large volume of work to be done, and there's also judgment to be exercised, and it's a tricky management issue how you propagate sort of judgment calls up and down kind of the chain of people who are working on this type of thing. At what point do you propagate? I don't know. Is this a I don't know, like if you're doing image curation, does this really count as an elephant, or is it a model, a plastic elephant? What does do we really call this an elephant, or do we call it a toy?
Yep.
And somebody, at some point, somebody has to make a decision like that, but you have to kind of propagate that to the point where that decision is made by somebody with appropriate experience and who knows how it fits together with the rest of the system. But the person who's actually looking at pages and pages of images isn't the one who has to be figuring that out all the time.
I feel like there's something like kind of philosophically profound about that. There's basically two types of jobs. There are jobs that have almost infinite scalability, and then there are jobs that don't. So, for example, being a musician now is one of these jobs that scales in the sense that some famous musician will go in a studio and record a song once, and then it gets played on the radio over the whole world to millions of people. Being a software engineer is also one of these scalable jobs where you can design some software that's used by billions of people with only, let's say a few hundred engineers, right?
Yeah.
And everyone is really worried about, say, automation taking a job that isn't scalable, like truck driving, and turning it into a scalable job. But in your case, you're kind of doing the opposite, where you are taking a job that had been done with, say, NLP, poorly, and you're changing the scale, changing that sort of dynamic to get something that has really high fidelity. And it's funny how even intuitively, like on the surface, I kind of, my first reaction is, oh, that doesn't scale. But maybe that's actually a good thing, right? Is maybe what we need is to have more of a human touch.
Oh, I don't know. I think the fact is, the thing to understand is, what does it mean it doesn't scale? The world is finite. When we started working on Wolfram Alpha, I had been interested in building something like Wolfram Alpha since I was a kid. I've been interested in kind of being able to sort of collect information, answer questions from it, and so on. I mean, horrifyingly, I found a bunch of stuff I did when I was like 12 years old, which is sort of pre-Wolfram Alpha stuff with, typewriter rather than, data centers, so to speak.
Mm-hmm.
But it's always upsetting in the sense. I don't know whether it's upsetting or satisfying to discover one's really been doing the same thing all one's life. But anyway, I was interested to, I've been interested in kind of, can you make computational knowledge real since I was a kid? And, I had actually always assumed that one had to kind of invent the whole of AI to do that. And eventually, as a result of a bunch of science I did, I kind of realized that wasn't the case. But when we started doing the Wolfram Alpha project, it was like, okay, let's take the team over to a big reference library and let's look at this reference library. And it's like, it's a big thing with, full of books. And my basic statement was, okay, over the next few years, we're going to grind all of the knowledge that's in here and we're going to make it computable. And, it's a daunting task, but it is finite. It's a finite sized room, so to speak. And we got much more knowledge than was in, the big reference library. But it's worth realizing that our civilization has only collected sort of a finite amount of knowledge about things. It's always surprising, the amount of sort of purely structured data that there is in the world is quite big compared to, for example, the text content of the web. I mean, I don't know whose estimate you want to take, but let's say the web is, I don't know, some modest number of tens of billions of pages of text. There's actually much more of that in structured data that even we have for Alpha. But so in other words, even if you say, well, gosh, let's use the scaling of the web and try and deduce knowledge from it, there actually isn't that much there.
That makes sense. Yeah.
And it's but I think for me there are two big multipliers that go beyond the sort of curate the data type thing. One is knowledge about computation, knowledge about algorithms, how you compute things from that data. Because actually, most of the time, people don't just want that one number that was sitting in a database. They want something that was the particular thing they wanted to know that is computed using some method or model or algorithm or something from the raw data that might sit in the database or whatever.
Right, or they're even looking for some signal. They want to decrease the entropy. So, for example, They have a bunch of sales data and they want to know which countries are outliers. So they want some decision tree that's going to say, this area of the world is performing great, this area of the world is performing poorly, and they want some system to extract that high level information.
Right, but you see now, take that example. It's an interesting example because it's an example where the kind of knowledge-based approach that we use in Wolfram Language is important. Because let's say you've got that raw sales data, you've got the table of numbers, you've got the number for Luxembourg, you've got the number for Germany, you've got et cetera, et cetera, et cetera. On its own, those numbers aren't all that significant because if you don't know, let's say, the population or the GDP or the number of internet users or something in each of those countries, it's hard to make all that much from it. And so it becomes really important to have good computable data that you can use as part of the kind of pipeline of actually doing things. And you could say, well, I'll go scrape that data from somewhere. Okay, great. Then you scrape the data, you discover that countries that have spaces in their names don't work,
right,
et cetera,
right.
et cetera, et cetera. I mean, it's and this is this is what I've been trying to do, is to kind of add this kind of layer of kind of automated computational intelligence that people can kind of take for granted in computing things. I mean, the way I see it, if I look at kind of the longer arc of history, back from like 60 years ago and so on, when the first computers were coming out, it was like, well, you could take for granted the fact that there'd be some what was called a high-level language like COBOL or Fortran on that computer. Then a few years later, you could take for granted there'd be an operating system on the computer. Then a few years later, take for granted there'd be some kind of user interface or some kind of networking support on the computer. And what I'm trying to do, basically, is to let people take for granted a sort of layer of computational intelligence that they can expect to find on a computer. And where we've tried to take sort of the knowledge that our civilization has accumulated and try to sort of inject that as something that can be automatically accessed by anybody. And that's kind of the bigger picture of what we're trying to do. And sort of a couple of branches of doing that. I mean, in Wolfram Alpha, we're trying to make a sort of consumerized drive-by version of that, where you just ask a question with natural language. You can, ask it by voice, since, through intelligent assistance, or you can type it on the website or whatever. And the, natural language, like let me ask a question, like, what was the population of France in 1952 or something? That's something one can easily ask as a kind of natural language question. And that's what we're doing with Wolfram Alpha. With Wolfram Language, we have a precise language in which a question like that can be expressed. It's very simple to express, but in which one can build up much more sophisticated kinds of things, in which one can sort of represent. It provides a more precise way than human language to represent what one's talking about when one thinks about things computationally. I mean, a way to think about this that sort of emerged recently is when we think about contracts. People want to say, I want to say precisely what's going to happen. Well, they try and write it in English. Actually, they wind up with some kind of legalese that's some kind of very stilted English often. But what we're trying to do is to make it possible to say what you want to have happen in code, in precise computational language code. But that code, in order to talk about what you want to have happen, it has to be able to talk about things in the world. I mean, it's no good to just say, okay, I'm going to declare that there's an array of integers of length, whatever. That's not really good enough. You have to be able to say, if the person is more than 50 miles from this place, then whatever. And that requires that you understand geopositions and distances and, all this kind of thing. You have to actually understand stuff about the world to be able to express these things. But what I've been trying to do is to make a language in which you can express those kinds of things, but you can do it precisely, and you can do it in a way where you can kind of build up, many layers of complexity. So, in a typical, when you interact with Wolfram Alpha, it's like, the typical thing will be, a fragment of a sentence or maybe a whole sentence. When you look at what people do with Wolfram Language, there are, well, probably the biggest code base we have. I don't know what our total. I know Wolfram Alpha is about 15 million lines of Wolfram language code. I think our whole Wolfram language code base, which is mostly written in Wolfram language now, is around 50 million lines.
Hmm.
So it's rather dense code because it's very very high level symbolic representation of things. But so kind of the idea is that one be able to my goal is to give people sort of a to be able to let them sort of in every line of that code make use of all the knowledge that our civilization's been able to accumulate, and don't have to build everything kind of from the sand up, so to speak.
Yeah, that makes sense. I think it's fascinating. One of the things that I've felt in the past is the way, and then I'll jump to something else. But the way Google has sort of crawled the web, it's really kind of, I mean, it's a great service, but one of the issues with that is the data, as you said, hasn't been very structured, and other people haven't been able to play a role. Even though you might not have volunteers, but you're still going out to these data providers who are ultimately going out to the actual source of that information. Mm-hmm. And there's this sort of two-way conversation. And I think that adds a lot to the richness of the data, which I think is awesome. How do you deal with, let's say, questions around saliency? So if someone wants to say, tell me something interesting about my profits in the past 10 years or something like that. Like, how do you avoid, how do you take into account someone's mental model? So when they ask something, it's not just sort of a laundry list of details, but you kind of take into account their intuition there, right?
Right. I mean, it's interesting. When I started working on Wolfram Alpha, I kind of designed this framework for figuring out, okay, so what does the sort of automated report that Wolfram Alpha generates look like? And I thought we're going to have to iterate this a zillion times to make it, useful to people. Turns out, with a bunch of fairly clever heuristics and things, we do remarkably well. And, because we obviously have data on what people click on and, where they read and so on. And, I think but it requires, expert knowledge to build these things. So, I mean, those heuristics are built by using the fact that, somebody who actually knew a lot about this field helped define those heuristics. If it was just like, let's automate it, let's try and put a ranking algorithm in here and just do it based on, we don't know what this is. It's just a question of how the words are correlated. And, let's use, TF-IDF or something to do something. Mm-hmm. It's turned out that was actually, of all the various things, it was one of many things that I thought was going to be really difficult with Wolfram Alpha that turned out, we had a bunch of big advantages in terms of the way our algorithmic system the framework was built, and also the kind of way that we made use of, experts all the way through what we've done. But that turned out to be making reports that are what people care about has turned out to be remarkably, that has not turned out to be the difficult thing. Now, if you say, okay, let me, throw me some random data, tell me something interesting about it. We actually have done that a bit. We actually had the pro version of Wolfram Alpha. You can actually upload data sets and it will try and do things like that. I don't consider that particularly successful. I mean, I don't think people find it amusing, but I don't think it's, I don't consider it kind of something that is a core thing that people really care about at this point.
That makes sense. I mean, I think it's profoundly difficult to come up with some kind of distance metric there. Like if someone gives you a bunch of financial data and you just project that into some latent space, you'll end up with some distance metric, but it probably doesn't match their mental model, and things that you
right.
think are really close or really important actually aren't.
Okay, so this, I mean, it happens to be something I've thought about a lot, is the theory of interestingness. So in other words, I've studied a lot kind of simple programs out in the computational universe, things like cellular automata and so on. And so you look at lots of these cellular automata and you say, which ones of these are interesting?
Right.
You look at them and some of them look, that's kind of cool. It does all these things, but which ones are interesting? Or you can do the same thing for chemicals, let's say. You can start enumerating possible, hydrocarbon structures, and you can say, which ones of these are interesting? So interestingness is a is a very cultural kind of thing. That
Yep.
is, what is interesting to somebody depends on, the whole history of how they got there. And for us as a civilization, when we say, well, what's interesting to invent, or what mathematical theorems are worth proving, those are things which are, very history and context dependent. And in fact, it's really so. Okay, in my world as a language designer, here's a way to think about this. So, you can imagine sort of concepts in the world, and you can say, well, which ones of these concepts are interesting? We see stuff, let's say, in the Stone Age or something, we saw, I don't know, different cracks in mud or something, or different kinds of puddles or something like this. And at some point we decided, well, puddles were interesting enough that we would give them a name. And so as human language emerged, somebody said, okay, that's called a puddle. And then, people could discuss puddles, and they could discuss lakes, and they could discuss other things for which they had names.
Right.
So in other words, there was sort of sort of condensed, this cluster of things in the world condensed into a concept that was interesting enough to be given a name.
That's right. And it's actually culture, as you said, it's culture dependent. The common, the one that everyone talks about is how Eskimos have, I think, 50 words for snow. And that's just because that snow occupies a big spot in their mental model of the world, right, because they see so much of it, right?
Right, exactly. But I think so what does a language designer do? Well, a language designer has to think about, what are all the computations people might want to do, of which there is sort of an infinite collection. And if you, as I've done, study the sort of abstract space of possible computations and so on, you realize there are even more of these possible computations to do. The question is, which of these are interesting enough to give them names, to make them primitives in your computational language, and to have people think in terms of them. And that's, that I think is the sort of, at a meta level, that is the role of the language designer, is to figure out, what are the repeated lumps of computational work that you should define as primitives and build your language out of. And what's really interesting to me is that when you build your language and you identify certain primitives and you give people this language, they will start thinking in terms of that language. And so, one of the achievements, I think, with Wolfram Language is that we've, lots of things have been invented and discovered with the language and with Mathematica and so on over the years. And I can't quantify it, but I think some significant fraction got discovered because we gave people a framework for thinking about things that was of a computational nature and that sort of condensed their kind of concepts into these things, into these kind of conceptual anchors that are the primitives of the language. And I think that's, and so the way that works, it's kind of an interesting spiral because as you build certain primitives, you get to think about things in different ways. And when you've thought about those things in different ways, then you can build another level of primitives. And we're kind of continually, in the history of sort of civilization, we're continually building these layers of abstraction as a result of having successfully sort of condensed our concepts into definite things that we give, for example, names to.
That makes sense. I mean, that's why, if you go back, I'm probably not going to get this chronologically right, but if you go back far enough, you get to the point where only the most brilliant mathematicians could understand geometry. And now you can't get a high school certificate without knowing geometry. And that's only because, as you said, we've compacted that and we've made that so innate and so unconscious that it can be broadcast to everybody.
Yeah, that's right. I mean, I think one of the things that one can think about education and the history of sort of development of civilization again is, as time has gone on, we know more and more stuff. And you might think, oh my gosh, that means we have to, people have got to be educated for 100 years in order to be sort of functional in the world because there's all this stuff to know. But the thing that's ignoring is the fact that there have been these moments of kind of where these kind of moments of unification and abstraction that happen that allow one to take something like what you're just describing. You don't have to learn you don't have to learn every theorem in Euclid. You can know certain principles of geometry, and that allows you to figure out a lot of things without having to go through every detail to get there. And but the thing that's important about that from the point of view of language design, computational language design, it's kind of the same story. It's like, what do you have to put into the language that gives people that gives people a framework for their thinking that lets them sort of make use of this process of abstraction. And as far as I'm concerned, people don't yet understand, the role of computational language in framing the way that people think about things. It's a funny thing because people talk about, the Sapir-Whorf hypothesis for human natural languages, and that's, the hypothesis that the words in your language define how you think about things, and people argue how valid is Sapir-Whorf, and is it really a significant thing or not, and that's there are sort of I think it's a real thing in human language, but it's somewhat weak in human language. In computational language, it's extremely strong. That is, the things you think about, we've developed in, Wolfram Language, we've developed sort of a way of thinking about things, and you can kind of see that people, I know for myself, and I can see with other people who are kind of fluent Wolfram Language users, I would say speakers. It's a funny thing. Years ago, yeah. I happened to visit this group of, I think they were 11-year-olds at the time, who had been learning Wolfram Language, and very smart kids. And that was the only time I've ever heard people actually speak our computational language. And it was a very bizarre experience for me because, I invented this language, but yet I couldn't process it fast enough. I'm just not used to hearing it as a spoken language. It's nice. Very, very bizarre but anyway, I mean, people, it's interesting to me that, for example, when I'm trying to think about something and, I can start typing Wolfram Language code much faster than I could explain to you what I'm about to do. So that's what it's like to be sort of fluent in that kind of computational thinking, and with our computational language as a way of expressing that computational thinking, is the thoughts are forming, so to speak, around what will emerge as that language, rather than the thoughts are forming in a way that I could express in human natural language and then sort of translate into computational language.
That makes sense. What about, things tend to be moving towards, let's say, more of like these, what's the right word, like signal processing or statistical based approaches where you don't actually know anything atomic. You just throw a bunch of data into some layered, some system, some neural network or something that's just, this composition of embeddings, and then you cross your fingers kind of on the other side, right?
Yeah.
And so how does, with that sort of trending and people wanting to sort of automatically extract signal, where does Wolfram Language kind of fit into that? My guess is it sort of would provide a very nice sort of basis function or basis set of data that then someone can go and do that kind of thing. Or maybe it's that those people are totally wrong, and really the basis,
that's
is
I don't think
that's
quite the right way to think about it. I mean, it's the same as the way that we use. So for a long time, these kind of soft tasks, like identify whether this is a picture of an elephant or a teacup, those were very hard for computers. Mm-hmm. And nowadays with modern machine learning, that's rather easy. And so there are these tasks that had traditionally, these kind of soft tasks that had traditionally been very hard. And what's happened, if you look at how that's interacting with Wolfram Language, I mean, we happen to have a rather wonderful sort of highest level machine learning framework that people have right now, happens to be the thing we built on top of MXNet, which is a low level framework for machine learning. But the way that interacts with Wolfram Language is there's a function called image identify, and the innards of that function make use of all of this kind of soft neural net stuff. But at the end of the day, it's like, okay, we'll take 1,000 images and we run image identify on all of them, and then we start making histograms of how many rhinoceroses and how many eagles were there in those pictures and so on. So in other words, these kind of sort of soft things become elements of what is then ultimately going to be this big structure that we build. I mean, if we think about it in terms of the way that humans work on stuff. Again, let's imagine it's a legal contract. Somewhere in the legal contract, it will say if it's a ripe, if the bananas are too ripe, then they'll be rejected. Okay, and that, if the bananas are too ripe, that's a soft question. But
Right.
the whole chain of things around, then they'll be rejected, and then this payment will happen, and then that will happen, and so on. That's all sort of symbolic structure. I mean, if we look at it in terms of how we as humans act, symbolic structure is what we tend to represent, like in a conversation like this, with our human language. But there are other things that we do that are, the way that we automatically process things in our visual system, where we say, yeah, I'm looking at a bottle of water or something. That's something that is happening at that level. Now, there is an interesting trade-off that's happening right now so there's certain kinds of tasks where it's absolutely true. The best, a really good way to do it is you just give it a bunch of training examples, you let it learn. It's been interesting, what does it mean to do data curation in a world of machine learning? So, for example, we have this neural network repository, and the importance of that is that we are not there. The main thing we're learning is things like feature extractors.
Right.
So, and that is a very useful piece of curation. It is a piece of sort of the fact that we now have a really good feature extractor for images, or really good, getting a pretty good feature extractor for sounds, for example, as well. That then allows us to compute a lot of things, and that's kind of a different kind of data curation. I mean, just like when we were first doing sort of modern machine learning stuff, maybe 5-6 years ago, one of the big advantages that we had was that we were very experienced at doing data curation. So when it was a question of, okay, take all these images and figure out what they're of, it wasn't just, we'll just search the web and see what tags they have. We actually had good processes for being able to inject, some human knowledge into being able to do that. But I think there's another thing, which is sort of the trade-off between what is when do you have a model of things? I mean, so for example, is machine learning the end of science? Is an interesting question. In other words, one has been interested in physics, for example, in saying, let's write down some theoretical model for this process, and let's work through that theoretical model and see what consequences it has. That's sort of, way number one for doing it. Way number two for doing it is say, let's just take a bunch of examples and try and machine learn the results. So for example, let's say you're trying to work out, that sound your washing machine is making. Is the washing machine about to blow up, or is it perfectly happy? Well, one approach you can take is to use, like we have this whole systems engineering system. You can actually have some sort of engineering model of your washing machine, and you can try and compute from it the resonant frequencies and work out vibrations and so on, and figure out what's going to happen to your washing machine. Or you can just say, let's just measure 10,000 washing machines and throw it all into a neural network and see what comes out. It's interesting. I'm not sure, what we're seeing, in people who use our technology stack, they can do both of these things with it. And it's interesting to see, in the last few years, there are some things where, the black box method is working really well. Other things where the black box method just doesn't seem to be making it. Yeah. And you actually need to kind of understand what's going on.
Yeah, exactly. I think that's exactly it. I look at it as sort of three layers. The bottom layer are what questions. So, here's a washing machine. What will happen today? Will it break or not? And so you can take thousands of washing machines. You can say these ones broke today, these ones didn't. You have a bit of a sampling problem. Let's say take millions of washing machines, and you can figure that out. And automated methods are getting very good at that, right? But then if you move up, the next level are kind of how questions. They're control theory questions. And so I feel as if when you do the pure automated way at the bottom, and then you try to do control on top of that, it becomes very difficult because you don't actually know what you're controlling. because those signals are not the signals are just effectively coming from noise. You don't know the difference between that data and noise. And okay, you've extracted signal from it, but now you're trying to control based on that. And then the top layer is causal analysis. So why am I even taking this policy? Why am I even doing this controller based on these signals? And you end up sort of kneecapping or handicapping yourself when you do too much automation, too much unstructured learning at one of those lower layers. You make it impossible to build the layer above it.
Well, I mean, one way to think about this is if you ask, is there a role for kind of computational language, for symbolic language, or should we just throw everything into, a black box machine learning system? Well, if you look at the difference between humans and other animals, you kind of see what the payoff is for symbolic language. That's the way in which we differ. Yes, you can get your average beaver or something to do many of the tasks that we can expect to do without this construction of symbolic language that allows us to express abstract things and so on. There's a level that you can do and which we were unable to do with computers properly until quite recently, but now those become components in what in our sort of human development has been all the stuff we've built. Our civilization was made possible by this idea of symbolic language and by the idea of being able to express abstraction and so on. And that's in a sense what someone like me is trying to capture in the computational language that we're building. I mean, what's interesting about the computational language is it's kind of another level of sort of communication. I mean, in other words, when back in the day, there was the most basic level of communication for life is genetic. You pass to your offspring certain information. Then there's things where sort of things are automatically learnt in each generation, like your visual system learns from the actual objects and correlations it sees in the world. Your visual system, just like a neural net, learns how to see, so to speak.
Yep.
But then the big innovation of our species is that we get to actually communicate stuff from one generation to the next using sort of abstract symbolic representation of ideas. But still, we're kind of stuck because, one generation can write the books, the next generation can be like, oh, we don't understand the books, or, when you talk to somebody, it's like you form the thoughts in your brain, you express those thoughts in human language, but then the person on the other end has to do a whole bunch of work in their brain to absorb that language, to fit it into their thought patterns, to be able to take action on the basis of it. The thing that's pretty interesting in terms of computational language is we don't need that second step. Once we've expressed something in computational language, it is immediately executable. And that's and so in other words, when we're the way I see that in terms of sort of the AI world is we get to, instead of just having to, we could like talk to our AIs in human natural language, and we can try and say, yeah, we want you to do this and that and the other, and the AI can try and figure out what one's talking about. Or one can, if one has a good way of expressing sort of one's human goals in a precise computational language, and you just say, okay, here's what I want to have happen. Now it's up to the AI to figure out how to make that happen in the most efficient possible way, but you've expressed what your goals are in a precise fashion. I mean, I think that again, in a sense, the role of automation is, humans define, what you want to have happen is humans define what they want, then it gets actuated as automatically as possible. But a piece to that is humans have to define what they want. And now that, with computation and AI and so on, the set of things that we can get done automatically is very broad. There's a big focus on, so how do you tell the AIs what you want them to do? And that's why I care about computational language, is that gives us this bridge between our human goals and human thinking and what we can get computers, computation, and so on to do. And that's that's why I see it as being a pretty important thing in kind of the history of kind of developing kind of sort of the trajectory of human civilization. It's an important moment that we're at right now, where we can automate a very wide range of things. The question is just to say, what do we actually want, and then to be able to describe what we want. And that's we have a program for middle school kids, and I think the tagline, last I knew at least, the tagline was, "Who's going to tell the AIs what to do?"
Nice.
And it's I think it's an interesting thing in terms of education and what people should be learning about. I mean, this idea of sort of thinking about things computationally is, this is the really important thing of this time in history. I mean, we are the sort of the 21st century is the time when the computational paradigm basically took over everything.
I think one of the things there is I'm seeing a lot of research lately around these generative adversarial networks, right? And so the idea there is you want to project things into some latent space. That was sort of the big thing of, let's say, the last decade or the last 5 years, was this sort of compositional embedding and how powerful that is. And a lot of the unsupervised methods got kind of wiped out by deep learning, right? Now you're seeing sort of these approaches to try to reverse the process. So you'll see, for example, someone will use a GAN to generate endless amounts of birds. That was a research paper I saw. Or for example, they would use a GAN to reverse an embedding and generate a text description from a picture. So there's a picture of a person sitting on a bench that's in the test set, and the training set didn't have that, but it had a lot of benches and a lot of people, and the system was smart enough to sort of reverse that embedding and create language. But it's an extraordinarily difficult problem, and as opposed to images, where people have understood that convolutional nets and these things have really captured the regularity of images, we haven't really done that for language. And definitely the research should continue, but I think an alternative might be at the educational level, getting people to communicate with computers in a slightly different way. That might be the low-hanging fruit there, rather than trying to reverse engineer the entire history of human language.
No, I think you're right. I mean, I think that the human language is decently optimized for humans communicating with each other. Computers, we are in the business, we built this whole NLU system that, is used in Wolfram Alpha, that's in the business of taking the random things that people say to their phones or their, cylinders in their kitchens or whatever, and trying to make sense of those. And for small utterances, we can do quite well. For building up a whole complicated story, you could do it, but it's really a pretty silly way to do it. Now,
right, and the state becomes a big problem. So if someone says, you hear these people will showcase these examples, but they're always very contrived. So someone will say, Google was showing this off at one point. Someone would say, what time, or what's the movie with this actor? And they would say, I don't know, Black Panther. And the person would say, what time is that? And that subsequent query would have the context of the first query.
Yeah,
you would know, but it's so hand coded. You're getting a system to keep state of the conversation in an automated way. No one's even come close to that, and we expected so much more progress than we've got as a community. That might not be a good problem to be solving.
Right. I mean, so here's an analogy. So back 500 years ago, literacy was not common, right? Written, people didn't know how to read and write. So certain kinds of things could be expressed by, spoken things. People had to memorize. They're probably better at memorizing things back then. But, there was a time when, for example, if you longer ago in history, like with lawyers, they would read the law. Somebody would not read it. They would recite the law. They knew every law, and they would just recite the law to decide whether somebody was doing the right thing or not. Then when literacy came in, it enabled a much greater level of sophistication and richness. You could create things that were much more, you could write books and many people could read them and so on. I think that this whole question about whether it's human natural language is good for expressing certain kinds of things, but when it comes to building big structures, it's not very good. If you imagine doing some big piece of software engineering where every piece of it was written with human natural language, it really wouldn't work very well. Now, a couple of things to say about that. So one thing I found really interesting. So, I worked on Wolfram Language for, 15 years or so before I started working on Wolfram Alpha. Wolfram Language is a very precise language. Everything is precisely defined and very, there's a precise meaning to everything. Then I started working on Wolfram Alpha, where the idea is people should just talk to it and say whatever they want to say. And there's no documentation. It's just like, it's our job just to understand those weird things that humans say to it. Okay, so I decided to adopt a completely different design philosophy. So in Wolfram Language, one of the things is I want everything to be as consistent as possible. I want to minimize concepts. I want to have everything be sort of infinitely factorable and so on and so on and so on. For Wolfram Alpha, it's just a pure do what I mean type story. And it's just like deal with whatever crazy things the humans say. Okay?
Right.
So it was interesting for me because those were two very different design methodologies. And it took me a little while to get used to the second one. But then, I used to be very afraid of heuristics. I used to say, never use heuristics. It's crazy. And then, in Wolfram Alpha, it's all heuristics. It's like, what does a human mean when they say, 50 cents? Oh, they mean something about money. If they say 50 cent, they probably mean a wrapper.
Oh, yeah. Right.
It's very, but if they say 47 cent, that's probably a mistake for 47
right.
cents. So it's just all heuristics. Right?
Doesn't that, I learned when you said that example, it made me feel sort of agoraphobic, right? I mean, it just sounds like there's an endless amount of, there's no end to the amount of things, the heuristics that you need to add to the system, right?
Well, yes, that's what I thought, right? I thought, oh my gosh, the thing's going to drown in heuristics, right? But what I learned after a while is there's a logic to heuristics, and yes, there are lots and lots of them. I mean, for example, if you're into software quality assurance, doing SQA on natural language understanding system is one of the scariest things you can do in that business because nothing is modular. Mm-hmm. The whole system. You can end up if there's a new wrapper who comes on the scene called 47 cent. That just blew up a bunch of your NLU for financial transactions and so on. So it's a very, very weird thing. But the point, when in working on Wolfram Alpha, it was just this heuristics, the logic of heuristics. Working on Wolfram Language, it's the sort of very precise, very sort of formal way of doing things. And I didn't know, I thought these were two different branches. Very interesting thing happened a few years ago when we started to basically build Wolfram Alpha capabilities into Wolfram Language. What I realized is that there are little fragments of when you write code and you need a list of the US states, for example, you just say control equals list of US states. That's a natural language. You hit return. It turns that into a precise symbolic representation of that then becomes something precise that you can use in your program. And so what ends up happening is there are these little fragments of natural language that you use for things like that. You don't say, map this pure function over this using natural language. That's a total lose. But you do say, give me the list of state capitals in the US or something. That you can say with natural language. So there's this interesting sort of connection between these two things. I mean, it's worth realizing that the software engineering stack that you need to make all this stuff work is somewhat complicated because when you're dealing with, for example, the thing I just said, let's imagine you're mapping over some list of state capitals. Okay, that list and you're doing it in some, version of Wolfram Language that's sitting on a desktop computer. that list of state capitals lives inside our knowledge base in the cloud. It has to, it's a sort of language where things, it's a language where it can make use of this kind of vast pool of knowledge that exists in the cloud. It's downloaded, sort of magically downloaded and cached, and all those wonderful things. But it's sort of interesting that, again, that's a different kind of software engineering experience, so to speak, to what one might be used to with, that's just a language and it compiles into machine code type thing.
But it seems like that whole concept of, I wonder if you need to, if the programming language needs to be attached to this sort of common sense reasoning database, or maybe they do have to be attached, but my guess is there's probably a large use case where somebody has, because the vast majority of let's say someone's building an app, the vast majority of their app is going to be written in a specific language, and that language is going to be designed around showing buttons and showing, sliders and things like that. But then they could take advantage of this sort of knowledge database and this knowledge language. It could almost like be embedded into any process that someone's doing. Right?
That's the less interesting way to do it. Okay.
All right.
Yes, we have a great way of making instant APIs where people can call us just for little bits where they have figured out that we can do them. What's much more interesting is to think about everything you're doing in this kind of very high level symbolic way. And because you get to do a lot more. Like, let's say you're laying out those buttons. Okay, well, we have a symbolic representation for, a user interface that's completely programmed, that ever for the last 20 years or something has been a completely program manipulable thing. So it's something where, you could write, hard code to lay out these buttons in this way, but you can have a symbolic structure that is, computed with nice functional programming sort of on the fly that does that button layout. And being able to think about that, or you could say, make the buttons be, I don't know, let's say a crazy thing, let's say you're putting buttons to represent which city you want to go to next. Well, you can actually use geographic data to place the buttons in your interface. It's kind of a stupid idea, but the whole point is,
it could be interesting. I mean, maybe you have a spinning globe or something like that.
Yeah, right. But I mean, the point is being able to, the big thing with Wolfram Language is it's free to do fancy stuff. With most, if somebody says, oh, by the way, I've got, I'm going to have 10 cities, and let me do a traveling salesman tour, through those cities. And somebody say, oh my gosh, I got to figure out how to write this traveling salesman
Download
thing.
A library. Sometimes library doesn't work.
Right. But the whole point is, for us, it's free to do that stuff. It's just sitting there. It's just some function that does it. And by the way, you asked much earlier about sort of the trade-off between writing things in low-level languages and writing things in, a knowledge-based language, that like Wolfram Language. Here's what I found. You imagine you were writing an algorithm. Let's say it's some numerical computation algorithm, and you're going to write it in a low-level language. Okay, but some point in that algorithm you say, gosh, if only I could do some algebraic analysis of what's going on, or if only I could use some piece of graph theory. Well, you don't do it if you're writing in a low-level language because it's just too hard to get that done.
Yep.
What ends up happening in our language, and what's been probably the last decade or so, most of the algorithms that we've produced, and we create a lot of algorithms, their building blocks are these very sophisticated things. And the fact that those building blocks are kind of freely available is critical to having a much more sophisticated level of algorithm than you could achieve if you were building it kind of from the sand. And by the way, the whole question of, is it efficient? The answer is, gosh, if you're doing, let's say, solving a traveling salesman problem or something, we have the world's best traveling salesman problem algorithms. Mm-hmm. You don't have to go, if you were writing that from scratch, you'd never use the world's best such algorithms because it'd be a big pain to try and figure out how to do that.
Yep.
Then the question is, how good can our compilers be? And that's because that's the big thing. Back in the day, people used to say, when I started doing computing, people would say, oh, if you're doing something serious, you've got to write an assembly language. These languages like C, they're crazily inefficient. But of course that's not true anymore, because optimizing compilers typically will do better than a human writing most humans in most situations. It's just not a good idea to write the assembly code yourself.
Or even another way of looking at it is the limiting factor now is the person's time and energy. The people, that's the commodity that doesn't scale. You can get a really large data center, but you can't necessarily take someone's mental model and replicate it to 10,000 people, right?
Yeah, right. But I think more than that, and what happens, because we've built this kind of sort of language at a different level than people have tried to build languages before, what happens there is there's just much more stuff automated. So people who end up getting fluent in the language can just be much more productive. They can write, it might take, 5 lines of Wolfram language code, or it might take, 200 lines of some other language. But by the way, calling on 5 libraries that you then have to figure out, well, are they really going to work, and so on and so on and so on. So, I completely agree. I mean, one of the things about Wolfram language is, my original idea is, pander to the humans, not to the computers. Back in 30 years ago or more, particularly when I was starting this, everybody was saying, oh, you have to make it easy for the computer. I'm saying, no, actually, make it as easy as possible for the humans. And the ultimate version of that is find a way for the humans as easily as possible to express what they want in computational terms. And then it's up to us, the implementers, to try and make that run as efficiently as possible. And, it's lots of work. And, like we're just building a very elaborate new layer of compilation technology to basically take this sort of very high level language representation of things and really, turn it into LLVM and, really have it grind all the way down, so to speak.
Yeah, that makes sense. But I think so most people, let's say, like they have some system, maybe it's a service on the internet, or maybe it's an app, or it's a website or something like that. And so they can interoperate with Wolfram language. But you're saying that over time, Wolfram language can eventually be used to drive, apps and UIs and things like that.
Yeah, and it is right now. I mean, it's used in lots of large-scale enterprise applications. They are just running Wolfram language code. I mean, they have some web server in the front end, and then behind it is, let's say a private version of our cloud technology, and it's just running, Wolfram language code. And that's, there's lots of that. It's kind of always funny to me. I go to, I go to a pharmacy and I pick up a prescription and I realize, oh my gosh, it's our technology that actually created, the thing that I'm seeing here, that went from, the doctor's prescription, written out, to the kind of symbolic representation that's used to compute all kinds of things about, multiple drugs or whatever, and to compute, the schedule. And, in the end, that label is probably, there's probably some piece of Wolfram language code that made that label, so to speak. It's
That's
a weird
cool.
thing in the world because, there's an awful lot of stuff now that, in the past there was a lot of stuff where the R&D was done with our language. Now there's an increasing amount of stuff where the actual deployment is done with our language. But it's a strange thing as a language designer. You realize, gosh, it's our technology underneath there. And it's like, and so what? I'm still, standing in line picking this thing up, and it doesn't make any difference. I mean, it's. I also find it interesting. The flip side of that. I'm interested in sort of education, and we should talk about that a bit because I think there's some worthwhile things to say about that. But so I end up quite often, talking to groups of kids and things like that, and a lot of them use Wolfram Alpha. And they kind of, they notice my name, they know about Wolfram Alpha, and there's this moment of surprise when they realize that there's a person who is connected to this thing that exists on the internet and that they use every day.
That's right. There's a real building and set of people behind all of these websites. They're not just ephemeral.
Right. And it's like there's a human and somebody decided to do this and somebody actually built it.
Yeah. How is Wolfram Alpha answering questions when you're here?
Yes. Right. We did that as an April Fool gag at one point. We had a handwriting output from the thing, and we had a whole backstory about that.
Nice.
But I think in terms of sort of the educational aspects of things. I mean, this whole question about you talked about, what's the right way to do things? Is the right way to have computers kind of come and understand human natural language, or is the right way for humans to get to the point where they can express things in a more computationally precise way? And I think the thing, I was talking about sort of the literacy transition 500 years ago. There will be another such transition. And it will be a transition where where the typical person understands computational language. And I like to think that the things I've spent much of my life building will contribute to that, that people will understand enough computational language that they can routinely express themselves in that way. They can write that little contract. They can define, the restaurant menu will be in computational language, and they can say, well, actually, I want to make a change to this. Let me, change that piece of code, so to speak.
That makes sense. It's sort of like solving a maze by, beginning at the start and the finish and working your way to the middle. If we make it way too open-ended for the people, then there's just too much ambiguity. On the flip side, we can't expect everyone to write C code to order a hamburger, right? But there's probably a spot in the middle where people think and act, people interface with computers with much more unconscious knowledge, similar to right now how we can use algebra almost unconsciously, and that will help the whole process tremendously.
Right. No, I think that's, as I say, the language design is a curious kind of art, because it's not like it's all about kind of trying to think about how people think about things. It's not like doing basic science where you are purely trying to do something abstract, and you have to be thinking about how does this relate to sort of what people care about, how people think about things, and so on. And I think in one of the things that's really neat right now is that through the technology we built, the world's fanciest research scientists and so on, a very large collection of them use our technology to do their work every day. And it turns out that exact same technology is now perfectly accessible to middle school type kids who can learn sort of to express themselves computationally in our language, and who can, by the way, do things in the language that they immediately care about. So it's not just this kind of abstract exercise of, write a program that sorts numbers or something.
Right.
They can say, let's take movie posters of the popular movies of the last year, and let's find out whether red is becoming a more popular color or whatever it is.
We always laugh about the, if someone's applying to be a data scientist or which is basically Silicon Valley's version of just statistician, right? But if someone's applying for one of these roles, they'll do a coding interview where they'll have to sort a list or invert a binary tree or something like that. And it's kind of funny to see someone with, say, 20 years of experience, inverting a binary tree, and it's just kind of a running joke. But maybe that's because there's sort of this inertia, and maybe something better would be using a language that allows you to fetch a lot of information and solving a much more high-level problem.
Right. So I mean, a typical one that we've used a few times is okay, you're given a lat-long coordinate on the Earth, and you're going to produce a map. There's a real problem in Wolfram Alpha. You're going to produce a map. What's the default map scale that you should use, given that you're throwing a particular lat-long coordinate on the Earth? Okay, if the lat-long coordinate lands in the middle of the Pacific, you obviously don't want to show a 1 mile radius map. If the lat-long coordinate lands in the middle of Manhattan, you probably don't want to show a 1,000 kilometer radius map.
Yeah.
And so the question is, what do you actually do? And so the answer might be, well, you look at the population density, you look at the actual imagery in the map, you try and figure out density of that. That's kind of typical sort of computational thinking problem. And the whole point of our language is once you can define what you want, like you say, I care about population of people, I care about, the entropy of the actual map features, or I care about, you can invent lots of different kinds of things, then it becomes pretty easy to express those things and to try out your algorithm. And that's a very different kind of exercise than the typical kind of computer science sort of list type thing. It involves different kind of thinking. And by the way, it's thinking which is not really taught much in a lot of computer science education. I mean, this idea of let's just think computationally about real problems in the world, that's not what ends up being in those computer science exercises. I mean, one of the things that is my biggest fear actually about modern computer science education, particularly at the K through 12 level, is that it'll go the same way as things have gone with math. I mean, what happened with math, most people's takeaway from studying math in school is, I don't like math. It's kind of boring. It's very, it's intricate, it's mechanical, it's kind of, why do I care? Like I've asked many kids with quite sophisticated kids, I say, the math you've learned in school, have you used it anywhere? And they're like, no. And that's kind of, so they learnt it as I've got to, do my algebra, calculus, whatever. And I'm doing that as a sort of separated abstract thing. And it's something where I'm going through the mechanics of it. I'm learning how to factor a polynomial, how to do an integral, whatever. That's like to the horror of particularly one of my kids.
Yeah, one of the things that cracked me up when I was taking the SAT as a teenager was there was a question where somebody had 17 watermelons and they were at a grocery store and the answer ended up being 17, and it was just, I found that hilarious because I just pictured this person with 17 watermelons in a shopping cart in a grocery store. And that is the stereotypical math problem. It's just, even in that environment where you had every opportunity to put, bottles of water or something, but they chose something even more absurd than that. And it just shows how disconnected it is from anything real.
Right. I mean, look, I think that a couple of comments about that, but I think, programming, low-level programming, I think is the enemy of computational thinking in education. That is, if what you do is teach people how to write quicksort, you are, maybe you don't even get to that level, but if you teach them how to,
do a for loop or something.
Yes, right. Most people will find that kind of boring. Some people who might go on to be systems programmers will find it super interesting. And that's great. And, but most people, just like all those people who won't go on to be pure mathematicians and who find a lot of the, algebra stuff kind of boring, will similarly be turned off computation by being fed this kind of very, very low level kind of why do I care type stuff. And I think, computer science education has gone through about 4 waves over time, the basic wave, which was one of the better ones, by the way, and then a series of other waves. Mm-hmm. And, one of the things that, I put a fair amount of effort into, although education is such a fragmented area, it's so hard to know really, it's easier in smaller countries, actually, where there's more central kind of decision making, but in a country like the US, it's really hard to sort of put effort and get commensurate returns. Mm-hmm. But it's this thing about, okay, let's teach computational thinking and let's teach it by having people be able to sort of form computational ideas and then make it up to the job of the implementers like us to make it so that what the kids, to make it as easy as possible for the kids to actually get computational results. And it's like, if the kids are getting the syntax wrong, that's not because the kids are stupid. It's because we haven't given the right user assistance prompts to make sure that they don't get the syntax wrong. I think it's whereas in math, you don't get to do that. You don't get to have, somebody thinking about how do we provide, algebra is algebra, and you don't get to say, oh, we're trying to automate this as much as possible so that the humans just have to do the real thinking part. It's just like, well, no, actually you have to, add, X and get 2X and all that kind of thing. And then you have to do that yourself. And I think, I think there's an important thing that happens in education there. I mean, it's for me, it's interesting. We run a summer camp for high school students, and we also have a summer school for sort of grown-ups that we've been doing now for 16 years. Where people come and do some original project that's never been done before, and they've often never done a project where you go from sort of nothing and actually create something. And it's really great with the tools that we have now. It has become there's an awful lot of low-hanging fruit out there. I mean, there's an awful lot of stuff where using our language, using the whole sort of computational paradigm, there are things that people can do. A high school kid can come in and in 2 weeks actually produce something really, really, really neat. You can, there's a website with all kinds of projects on it that kids have done. But that's something that is, it's a thing of our times that's possible. And I think that I find it particularly, for me, it's particularly cool to see that, these kids are able to make use of the same tools that kind of the fanciest, research scientists are using. And they're able to go find things that, are interesting new things, so to speak.
Yeah, let's talk about that for a minute on the accessibility side. So this is something we actually haven't mentioned on the show, but the vast majority of languages are just completely public, open source, and totally accessible. And the way that the people who put their time and effort into those languages support themselves is usually through some type of enterprise contract. So, for example, Java becomes really popular. Java's probably not a good example. Let's say Python.
No, it's terrible. It's an example of the disaster of what you're describing.
Yeah, it's like immediately regret my decision. So Python gets really popular. Anyone can go and download the source code and look at all of it. So in a sense, the intellectual property is the value there is questionable. But then some enterprise customer starts using it, and now they need to reduce their risk because they have a risk of something bad happening. With their system, that's a fault of Python itself. And so to reduce their risk, they spend money, and that's really what keeps that whole process moving. Now, I know for Mathematica, and I haven't, to be totally fair, kept totally up to date on Wolfram Language, but I know for Mathematica, it's similar to MATLAB in the sense that it costs money to sort of even enter and start using it. And so, how does that work? If someone's a student, how do they get started? And sort of what's sort of, I guess, the business model to some degree, and how does that sort of work operationally?
Right. Well, I mean, so I've been interested my whole life in kind of threading the needle of figuring out how to do the most interesting, innovative stuff for the world, and have that be sustainable over the long term. Okay, and I think I'm not doing too badly, in the sense that, we've been able to consistently be building, a technology stack for the last 32 years. It's interesting that when I started this, the first company, the first thing I built, I was originally going to sort of do the open source thing. I realized, gosh, there's no way to, that was in 1981. There's no way to support this. I have to start a company. I started a company of a certain kind, venture capital funded and so on. That didn't work out that well. I mean, the company eventually did an IPO and did okay, but it didn't work out well in terms of having a long-term sustained vision. For the last 32 years, I've been pretty lucky in that I have a smallish private company, only 800 people, mostly R&D folk, and we've been able to kind of keep innovating and building things. Now, the problem that we have, namely, build this huge computational language that has everything in it. It's not just one of these, I'm going to spend the weekend and come out with a new language
right.
and throw it out on GitHub type thing, right? It's a thing which is a sustained, in this case, 32-year story. and it's a story where I was pretty pleased. In the 30th anniversary of Mathematica, I thought, oh, let me see whether I can take code that I wrote 30 years ago, and there it was on an original Mac, and I could get it off with floppies and things like that. I take this code. This was just last few months ago. Take this code with great effort. I get it off the floppy and onto a modern computer, and by golly, it just runs in the latest version of Wolfram Language.
That's cool.
We have 30-year compatibility, and a lot of people in sort of the research world really appreciate this. I mean, they have stuff that they did 25 years ago, and it just works. And I think that the idea that my main goal has been sort of thread the needle of being able to do sustained innovative work for a long period of time and try and deliver something valuable to the world while letting as many people as possible use it and have the ecosystem work. And, we've done a variety of different things. So, for example, basically every major university in the US at least, and most around the world, has a site license for our technology. So for anybody at a university, it's free. I mean, the university is effectively paying an enterprise license, but that means every individual student and so on gets it for free.
Nice. So they put in their edu email address or something like that?
Yeah. I mean, supposedly the universities have ways that they distribute all these things, but yes, and that's basically what happens. Mm-hmm. Now Wolfram Alpha, the main Wolfram Alpha is just free to the world. There's a version, there's a pro version that students, some students, well, a lot of students end up getting because it has some additional capabilities like showing steps and so on for computations. But Wolfram Alpha, the idea was just make it free for the world. Now, then obviously we have an API that's what gets used by folks like Apple and Amazon and so on. And we have enterprise versions and all this kind of thing. But that's that's one model. Now, in terms of Wolfram Language, this is sort of interesting, actually. I mean, I have a very strong belief that one wants to have the source of funding for something be as aligned as possible with, where the value is coming is going, so to speak. So in other words,
that makes sense.
It's like the people who are actually going to use this seriously should be, if they believe in it and they're going to pay for it, then I don't want something where it's like, well, we'll make a free version, but we're really going to make our money off support. So let's not make the free version too good. Let's make the thing a little bit cockeyed so that we can make money from support, which is unfortunately what's happened. Or let's make everything free and get a lot of people to use it, and then say, oh, whoops, we got some patents on this. You have to pay up lots of money because you're using our patents.
Yeah, especially when it comes to documentation. I mean, it's like every line of documentation that you provide with your open source language is literally taking revenue away from your business model, which is to support people who are trying to use undocumented code.
Yeah, I mean, look, my point of view is I just want, I've tried to operate in a sense a very sort of, a straightforward business, so to speak. I mean, what we try to do is, continue to innovate and produce, the best language we can. Of course, the fact that we're doing this in an ultimately commercial way allows us to make use of all these data sources and all these other kinds of things, which there's no way they would say, if we said, oh, we're going to give everything away to everybody, they'd say, well, you can't give our stuff away. So, so forget having, financial data or something. Mm-hmm. So, it's part of the ecosystem that one has to have, everybody, it has to be a sort of a thing. The other thing is, there's the question of how do you maintain coherence? I mean, that's been my personal commitment, so to speak, for the last, 3 decades or so, is actually try and keep this language consistent and, do sort of unified development. And I think, it requires leadership to do that. I think, well, like Python, I gather recently had trouble with that because, it's like by the time, if in our case, I'm, in a position where I'm actually trying to lead this. Now, there's the question of source code. I actually don't really care whether, I mean, our source code isn't sort of publicly out on the internet. That's not something I care that much about, and I don't think anybody else cares that much about it either.
Yep.
Actually, for a decade, we actually had a large chunk of code, source code, out, freely available. And the thing that was really funny was, and we were doing this because we thought, oh, people are going to be interested in all these mathematical algorithms. Isn't that cool? Type thing.
Mm-hmm.
And it turned out when we finally did a sort of an assessment, did anybody care? We discovered that a large swath of comments in the code were in Russian.
Okay.
It happened that the people who were working on it was the people who natively speak Russian who work on this stuff for us, and it's like nobody read this for a decade. We had it out there. Nobody read this because somebody was said, "Oops, your comments are in Russian."
Yeah, I think the open source model makes sense when it's low level. So, for example, an operating system. If the operating system is not open source, then there's a worry that one day I won't be able to use my mouse or something like that. You could always write some interface driver. But for something like Mathematica, I agree. I mean, if I had to guess, I would guess that the source code is less important. What's more important is that somebody can make Wolfram Language a part of their process. So
right.
Yeah.
Right. And I mean, so what we're trying to do, I mean, I think we have a pretty good record of, 3 decades of stable, compatible, development, which I think is pretty impressive on the scale of languages.
Mm-hmm.
What I want to do, my goal is to have our language prosper, forever, so to speak. And, what's the best way to do that? I don't know precisely, but obviously, we want to set it up so that, whatever happens to our company, et cetera, the language will always be available, et cetera, et cetera, et cetera. Actually, a thing we're doing is so the Wolfram engine, which is kind of the core computational kernel of the language, we're actually going to be changing the way that's licensed so that it's much easier for people to incorporate it in things. And basically the deal there is going to be, if you're developing stuff, you can just use the engine for free. You can just download it for free. You can use it for free. As soon as you want a production license, if you want to actually go into production, running some big commercial site, then you pay us. But while
sense.
You're just using the thing to play around. Now, if your product is R&D, that's our traditional market, and that doesn't count as software development. But if your goal is, I'm developing this, I'm playing around with it, I'm trying to develop some product, then it's just there's a version that's free for developers. And I think I don't know exactly how that's going to work out, but
you're walking in some good footsteps there, because that's what the business model of Unity. So Unity, will give you almost everything, but then as soon as you want to make a commercial product, now in the case of Unity, they have a little bit more control, just because everyone has to, at the end of the day, package their game in a certain way. But I still think that this business model makes sense. The other thing that people don't really give a full appreciation to is just the and I might not be saying this correctly, but the sort of private, charitable nature of people. I mean, the vast majority of people recognize value and will pay for things. Especially if they're also making money, if it's part of their commercial process.
I mean, my attitude is there's, and we give away, our software to lots of, students and lots of different groups and so on. But like on the Raspberry Pi computer, there's a Wolfram Language bundled on every Raspberry Pi computer, freely available to people. And, there are lots of things like that. My goal is to make sure that the people who are really deriving value, and that value might be, doing the next great R&D thing, that value might be teaching a class, that value might be, delivering a product, the people who are really deriving what ends up being commercial value, support the continued development of what we're doing. And it's been, it's a complicated sort of threading of the needle, because I personally, if we had infinite commercial resources, maybe we'd be able to just give it away to everybody. But I actually think that isn't even healthy. I think it's good to have a situation where the people, who are benefiting are the people who are supporting continued development.
Yep.
And, that allows us, it makes us do things that actually make sense for the world, so to speak.
That's right. It's sort of like if you were to play one of these simulation video games like SimCity or something like that, and you give yourself infinite money, then all of a sudden the game becomes completely unguided. And so you have no direction unless you have some customers.
Yeah, the later versions of SimCity actually were a bunch of it was designed in Wolfram Language.
Oh, cool! I didn't know that.
That's just one of those. And I think the rules. I don't know exactly all the things that were done there. I've seen a bunch of the simulations of the simulations of the simulations of cities, so to speak.
Right. I saw an interesting article about how, not to go on too much of a tangent, but how they decided on the traffic model. And effectively, it's a Monte Carlo approach where they, at every time step, they randomly pick two different zoned places. So, for example, a residential zoned place and then a commercial zoned place. And they draw a path using the roads that the player has placed. And then they also then decrease everything by a constant so that they always have a distribution, a probability distribution. And over time, if many of those paths require the person to take the same road, then that becomes sort of a very nice mathematical model of the traffic. And to do anything like that, you need to try many different ideas.
Yeah, I'm quite certain that was prototyped in Mathematica and Wolfram Language. Just knowing the team that was involved in doing that. It's actually I have to tell a personal story about traffic flow, which is kind of when I was a kid, I was sort of interested in traffic flow as kind of a interesting kind of mathematical type problem, and I didn't really ever figure out terribly much that's interesting about it. Then I started working on these things called cellular automata. They're very simple programs that we just have a row of black and white cells, and you just have a rule that says if there's a black cell to the right and a white cell in the middle and etc., then do this. And the main thing that I discovered about things like cellular automata is it's very easy to get very complicated behavior even when the rules are very simple. Mm-hmm. And that turns out to I wrote this 1,200-page book called A New Kind of Science that is based on that idea, that actually just today came out in paperback. So after 16 years of being a pure hardcover book. But
oh, cool.
I digress.
Is it on Kindle or anything like that?
Oh yeah, and there's actually a free version on the web.
Cool, good to know.
Very, very elaborate version on the web, which and I've been slowly taking. Oh, this is a fun story. So all the the science for that book, the book came out in 2002, but all the science that I spent the decade before that working on for that book, it's all in Wolfram Language notebooks. So I wanted to sort of expose all that stuff, and so I've been just recently actually I've been doing. It's ended up that it ends up being me who has to do a bunch of this stuff because I kind of understand the code I wrote before. But so I've been live streaming some of these things, and I've been taking these notebooks that I made, in 1992 and things like this, and it's really satisfying because they just run. I just start them up, and press Shift Enter, and the code just runs. And some of it can be better now because we have cleaner sort of functions where we've used sort of higher levels of abstraction to define how certain kinds of things work, so the code can be shorter and clearer.
Sure.
But it's pretty neat that that all this sort of research notebooks that I had all just run. But in any case, I digress. I was talking about road traffic flow. So I studied these cellular automaton things, and then years went by, and I had sort of failed in my youth to be able to do much with road traffic flow. And then, then somebody said, by the way, there's this cellular automaton model that people have developed of road traffic flow. And actually, it turns out the standard model now is a cellular automaton model based on a thing called Rule 184, which is the 184th rule in this enumeration of rules that I made. And so it's like, it's kind of amusing for me because that's become, as I say, the standard model that people use for road traffic flow, and there it was, sort of right under my nose, these cellular automata that I studied, and but it's actually, if one's interested in sort of the meta theory of modeling, it's actually an interesting story, because what really happened, and what always happens with modeling is an idealization. So you say, I'm going to model snowflake growth. You might say, what really matters to me is exactly how fast the edges of the snowflake expand. But the fact that my snowflakes are circular, I don't care about that. I really just care about how fast the edges expand. Or I might say, what I really care about is the overall structure of the snowflake, and I don't care whether I get exactly right how fast the edges expand. So modeling is always as much about what you care about as it is about, you're never going to get all the details right, because models are always an idealization. And it's a little bit like what we were talking about a while back about sort of, what's interesting, so to speak, and the fact that that's very culturally dependent, so to speak. Mm-hmm. And so what really happened with this road traffic flow thing is that the things I thought were important about road traffic flow turned out not to be the things that are important. And what this cellular automaton model captures is a bunch of stuff that I really wasn't focused on. I was focused on various quantitative things that it doesn't capture, but what it does capture is the stuff that really matters for, modeling self-driving, modeling, current traffic jams and the effects of self-driving cars on them and all that kind of thing. But in any case, I think that was a digression. But,
no, I mean, one of the nice things about doing something, such as inventing a language or doing something, in the pure math space, or publishing a paper in graph theory or one of these things, is that it has just really wild implications that get realized over many years. I found out recently some research I had done as a student went into just figuring out the mass of a quark. And I know absolutely nothing about physics.
That's interesting.
I'd
be curious what that was. So I worked on particle physics when I was a teenager, actually, and it's interesting in terms of sort of the meta theory of fields, because I worked on particle physics in the late 1970s, when it was kind of the golden age of particle physics, and a bunch of new methodology had come in, and there was this like 5-year period when just there was major new result every 2 weeks type thing, kind of the same way that machine learning is today.
Yep.
And so what's interesting about being involved in a field during its kind of golden age of hypergrowth is that, there's low-hanging fruit lying all over the place. And so, I invented this thing, this way of studying the structure of particle events at a particle accelerator. And I was which I did when I was like 17 years old or something. And I was really pleased that, when the Higgs particle was discovered, they'd used these, as part of the kind of the pipeline of doing the analysis and so on. They used these things called event shapes that I'd invented. So that was, that's the benefit of being involved in a field during its sort of hypergrowth phase. The from a sort of career planning point of view, the downside is you've got a lot of competition during that period. I mean, if I personally tend to prefer working on things where, I can do neat stuff, but nobody else cares. And, and after it's done, my favorite thing, in a sense, is producing what I tend to call alien artifacts, things that nobody kind of thought would exist, but once it exists, you can look at it and you can realize it's interesting. So like Wolfram Alpha, I consider to be an example of kind of an alien artifact. Like people had they'd kind of tried to do question answering stuff for years, but they had not, they didn't have knowledge bases, they didn't have symbolic languages underneath them, et cetera, et cetera, et cetera. It hadn't really gone anywhere.
Yeah, I think the thing that I noticed about Wolfram Alpha is it's sort of a blending of two things. So there had been expert systems, like I talked about, OpenPsych, and there had been, there's WordNet. there had been these sort of Prolog, obviously driving a lot of that. There had been these systems, but they were far too rigid, right? And then on the other end, you have something like Google.com, which is extremely open-ended, but entirely data-driven, and there's no structure and there's no human intuition behind those results, right? And so I felt like Wolfram Alpha sort of walked that line very well.
Yeah, I mean, you mentioned things like Psych. Psych isn't. I had known Daglanat, the guy who created Psych from back in the early '80s, and so I watched that whole progress, and it was. I have to say, it was interesting because when Wolfram Alpha came out, it was. AI was at one of a real low point. I mean, people didn't really believe AI. 2009, AI was not. People said, I'm working on AI. It's like, oh, that's not going anywhere type thing.
Yep, I literally, my background is in deep neural networks, and in 2009, I got a job writing JavaScript because nobody needed someone who knew anything about neural networks.
That's good. So you're a data point.
Yeah.
No, I think, it was interesting when Wolfram Alpha was coming out, I had a friend named Marvin Minsky who was a sort of pioneer of the AI world. And I saw Marvin, probably a few weeks before Wolfram Alpha went live. And I said, Marvin, let me show you something, right? It's like, I said, it's a question answering system, among other things. And it's like, okay. And so, type a couple of things in, and then Marvin, changes the subject, wants to talk about something different. I said, no, Marvin, this time it actually works. And then he's like, oh, well, let me try something else. Oh, wow. And he's like, it was interesting to see because he really, he'd seen so many kind of fake question answering systems over the course of many years. He just decided it was impossible. And why were we able to succeed? Basically, I didn't really even understand this until sort of after the fact. I mean, as far as I was concerned in building Wolfram Alpha, it was just use what cleverness I might have and use and just do a bunch of engineering. But after the fact, I realized a couple of things. First of all, we had a lot of actual knowledge, and people have been trying to do natural language understanding and so on without knowledge. They've been trying to abstractly do it. It's just like, what's the structure? Let's parse the sentence and find the noun and the verb and so on. That's much, much less relevant than knowing this is a city and its population is roughly this and so on. And that's why it's likely to be talking about Springfield, Massachusetts, rather than Springfield, Illinois or something like this.
Mm-hmm.
And the second thing is that we actually had a target to turn the natural language into. Namely, we had our symbolic language that could represent things about the world. And another thing that, again, only became sort of clear after the fact is that a bunch of the, ideas about algorithm, what one might call algorithm discovery that came out of my new kind of science project, we used that a lot in building the way that Wolfram Alpha works. I mean, just to say something about that, I mean, the traditional way to think about building software is, or has been, let's write the lines of code to do what we want to do. What I ended up discovering from sort of just looking at, trillions of simple programs is that there are simple programs that do really interesting things, and sometimes those things are really useful. They might be good pseudorandom number generators, they might be good image processing things, and so on. And so we started developing this kind of methodology for just finding algorithms by knowing what kind of a thing you want, and then just going out and searching the space of possible programs. I mean, in today's world, that seems less surprising because with deep learning and so on, one's sort of doing the same kind of thing, although what we've done a lot more of is just exhaustively going out and sampling the computational universe, whereas in typical neural nets, you're doing this kind of incremental sort of more like biological evolution, taking small steps and trying to make sure the animals don't die on the way type thing, rather than just sampling the whole space. But I think that but to go back to the sort of the things about common sense reasoning and so on. So this project called Psych, which was an attempt to represent, to use essentially predicate logic to represent sort of facts about the world, common sense facts about the world. If something is dunked in water, then it is wet. Those kinds of things.
Right.
The When Wolfram Alpha came out, Doug Lennart said basically, well, you succeeded in what I tried to do, and the whole sort of common sense reasoning thing clearly wasn't able to get there. What I realized was a sort of interesting conceptual point, which is, in a sense, what Doug was trying to do was to use the state of sort of human thinking in the medieval time, in the Middle Ages. And I just cheated and used the last 300 years of science. Because for him, if he wants to figure out some physics problem with common sense reasoning, he's like, oh, well, if you push on this, then it'll push on that, which will make this happen. And it's kind of like you're reasoning through it, like you're doing natural philosophy to figure out what's going to happen in the world. For us, it's like, well, let's just use all that science that people have figured out. Let's just, for the physics problem, let's turn that into, Lagrangian mechanics and solve the differential equations and the answer is 7.5 or something. So essentially, we're making use of all that additional knowledge that's been developed in civilization beyond the pure human reasoning knowledge. And I think that's what, that's kind of, in a sense, we cheated relative to the original mission of kind of common sense AI. But
I think that the fact that you have these dynamical systems and they don't is definitely part of it. But I think the even more important part is the resolving of the ambiguity, ultimately through heuristics, but also through statistics and through language understanding and things like that.
No, right. I mean, look, it's just, as an engineering project, it's our effort was much, has been much more, pragmatic and in a sense, making use of many more methods. It not just saying we're just going to use common sense reasoning to figure everything out. We're using whatever method makes sense. And that's kind of a story, that's part of kind of the whole Wolfram language story, is put everything in so you can use whatever makes sense. When we come to do data science, for example, we like to talk about kind of multi-paradigm data science. It's just everything is there, so whatever makes sense to do, you can do, so to speak, rather than, oh, we've got a package that does this, so that's what we're going to have to do. But I was going to say, we were talking earlier about math problems and watermelons and so on. And one of the use cases that I really wanted to make use of sort of common sense reasoning for was math word problems. We still have never managed to do this. And it's, when you talk about, putting the watermelons in your shopping cart or whatever, and then somebody might say, I don't know, let's say you put the watermelon, you put the watermelons in bags in the shopping cart, and if there are X number of watermelons go in these bags, how many of them are still are visible as you're walking around the store? Well, of course, to know that it will be visible when you're walking around the store, you have to know that once a watermelon has been put in a bag, you can't see it anymore. And that's kind of common sense reasoning. Mm-hmm. And so to do, if you set up a word problem like that, you have to have a layer of common sense reasoning. We might be able to, if we can get an equation out of it, 3x plus 7 equals 14 or something, where x is the number of watermelons, then we're all done. Then we can just use, modern science, so to speak, to just crack that and get to the answer. Right. But the thing about, how many watermelons can you see in the shopping cart, that we need common sense reasoning for. Now, I've been hoping, that we'll be able to make use of what Doug has done for so many years. He's been very pessimistic about whether this is going to work. So it's never been tried. But and in fact, we can do basically up to middle school level math word problems using extremely boring heuristic template-y type techniques. We can't do We can't do more sophisticated ones, and it's sort of an interesting open problem to be able to do those. And it's a place where one might be able to use, well, one should be able to use, common sense reasoning. But it's interesting to realize that the space where there's sort of things that one actually wants to do, where sort of common sense reasoning is still worth doing, is a narrow space, and it's a space where, in a sense, those things were built for humans to have to sort of put effort in to figure them out. They're not natural things. I mean, another example might be,
that makes sense.
Let's say you're doing medical school and you're saying, which nerve goes near the such and such tendon, of such and such. Well, you could do that with common sense reasoning, but actually, we've got a complete 3D map of human anatomy, and you can just go and use computational geometry and answer the question. And it's not, even though a medical student might do it by thinking through, this goes that place and that place, and so they're using common sense reasoning, but that's not how we're going to do it with a computer.
It's interesting. It sounds like so. If you think about these word problems, ultimately what they're trying to do is they're really trying to do two things. One is sort of obfuscate the core problem, so they're not just giving you 3x plus 7 equals 14. Mm-hmm. But they're wrapping it in some narrative that you have to understand. So they're making the problem harder. But then they're also trying to relate the problem to real life, which is why it was so funny to see the 17 watermelons in one shopping cart. So in a sense, if you could generate relevant, if you could generate say SAT math questions that really connected with somebody, that would be maybe more difficult than the counting they would do at a real grocery store, but would closely emulate something they would do in real life. I feel like there's something really profound there. So, I mean, because you've sort of understood that it is truly a common sense reasoning problem. You've understood the way the routine things that people do and the math that people do on a routine basis. And you've been able to sort of extrapolate that to something more difficult, like differential equations, and figure out a way to sort of tie those two things together. That's actually something profoundly complex.
Right. I mean, look, I think that the thing one would like people to learn is the stuff they can't just feed to computers and get automated. And, the main thing is this question of taking sort of a human thing you want to do and thinking about it in computational enough terms that you can, describe it in a precise language and have a computer unambiguously know what you're talking about. And I think that process, I mean, when you talk about like math word problems, sort of the idea there is take these kind of fake situations in the world and try and mathematicize them. I think the real thing that people should be learning how to do, and very few people are actually learning this yet, is take things in the world that are real things in the world and learn how to think about them computationally and be able to express them in such a way that both you can think about them more clearly. I mean, the remarkable thing for me, at least, is, I've been spending years kind of thinking about things computationally. And so there are lots of kinds of, very everyday questions where I think about them in terms of breaking it down into the kinds of, structure that I would use to think about something computationally, and then by golly, I can actually get to an answer. And whereas otherwise you just don't have it, it's very mushy. You don't have a way to think about it. If you don't have this kind of framework, and in our case, computational language to use to think about things, you can't form them precisely enough in your mind to actually get to a conclusion. I mean, it's the same problem as Doug's common sense reasoning thing. You end up with you don't get it's kind of all it's all these if it rains then it will get wet, then this, but it's all very kind of vague, and it doesn't give you a precise structure to operate in. Talking of which, I think we're probably reaching the end of my I'm a creature of one of the things I'm a data oriented person, and so
yeah.
I do I've do a lot of sort of personal analytics stuff, and I was somewhat horrified a number of years ago to discover that I'm the human who's collected more data on themselves than anybody else. And so one of the things I know is that I get sleepy at a very precise time, and that time was about 10 minutes ago.
All right,
I'm
totally makes sense.
I'm going to start failing here, but
no, I think that's great. So I wanted to, I mean, this has been just absolutely fantastic. Thank you so much for coming on the show. I think people are going to be absolutely fascinated to hear a true programming language inventor, and to sort of hear your story and this dialogue. I think it's been amazing. What about, just to sort of conclude here, like we always ask two things. One is sort of, what is it like day to day at your company? So in this case, Wolfram Research, and are you hiring? If so, what kind of jobs are you hiring for? Where? Things like that.
Okay. So, I mean, for me, I spend most of my time figuring stuff out. It's pretty neat, actually. It's, I'm an unusual kind of CEO because I'm deeply involved in the design of the product and so on. And, we've got great people at the company. And so an awful lot of what happens at the company just happens and doesn't require, the CEO to stick his nose into those things. And in fact, in one thing that's been interesting the last year, but since we've been doing this live streaming of internal design review meetings, is that folks who want to know what it's like to work at our company, well, there's 250 hours of what a bunch of meetings are like that's out there in the archives of the live streamed stuff. I think that so our company is very geographically distributed, where our headquarters is in Champaign, Illinois. I have been a remote CEO for 28 years. I live near Boston, although I happen to be tomorrow doing my about 3 times a year trip to Illinois. But the thing that we end up having people kind of scattered all over the world. Actually, there's our HR department tries to maintain an accurate map on our careers section of our website of where people are in the world, and it's quite diverse, I would say.
Cool.
In terms of what the places we tend to not hire people in New York and Silicon Valley because we're going to that's super expensive for us, and it doesn't we don't really need the proximity to other things that Silicon Valley provides. Not that. I mean, it's. I think in terms of we've ended up with I would say wonderfully talented group of people from around the world.
Yeah, I know some folks who work at Wolfram Research who are in South Africa, and
yes,
it's amazing.
Right. I mean, it's I think that the thing that I really actually I've come to appreciate the sort of the diversity of having people all over the world in all kinds of different settings and situations and so on. It's I think it adds a certain vibrancy to what happens that is something I certainly appreciate. But it's we've ended up with lots of world experts on lots of kinds of things. We've had lots of people who've been at the company a very long time, and some people they're at the company for a decade, then they say, oh, the grass is greener somewhere else, and they go off somewhere else for a few years, and then they come back, which
cool.
is always satisfying for management to see that happen, so to speak.
Yeah, definitely,
because it means we're doing something right. But I think that the thing that we've ended up with. It's like people who are good at thinking are the people who tend to succeed, because we're always trying to solve a lot of what we're doing is stuff that's never been done before. And my principle in building the company is very similar to my principle in building our language: automate as much as possible. And so, for me, you mentioned JavaScript programming. There was a period of time when we had tons of JavaScript programmers, and it's like, look, guys, what you're doing is, why don't we build something higher level that just automates a bunch of this stuff? So we did that. And so then, those folks, moved on to doing other things. And, and for us, that they end up getting, being able to work on sort of higher level things. And for the company, that's how we get away with only having 800 people, is by the fact that we've automated a huge amount of what goes on internal to the company. And, we're trying to, we're using both the principles and the actual technology that we've built, like our, our testing system is, of course, all written in Wolfram Language. Our one of the more exotic things that we're now doing is writing our ERP transaction processing system in Wolfram Language, because we just got fed up with actually, we got fed up with some of these pseudo open source things, which actually end up costing way too much money. And we said, these don't even work well. Let's just build our own. And it's so that stuff is now in terms of hiring. One of the things I might mention is we have this summer school every year. It's usually about 70 people from around the world. That's a great collection of people. It's become a favorite sort of pseudo vacation for a bunch of our R&D folk. And in fact, most of the instructors at the summer school are alumni of the summer school, which reveals the fact that the summer school is our single sort of, we recruit a lot of people from there.
Cool. That makes sense.
It works really well because people come and, they often have never thought about, working for the company, and they come and, spend 3 weeks and they do a project and they get to know a bunch of people at the company, and we get to see what they do. They get to see what kind of, our approach to doing things is. And it's kind of, it's very, works well. But I think in terms of what are we, I mean, we're always looking for, very talented people. I would say that my approach to management tends to be, we've got a lot of projects we want to do. We've got a certain pool of people that, have lots of talents, and sort of the role of management is to solve the puzzle of how do you connect, the talented people with the projects that you want to get done. And so we're more interested in kind of, really talented people than we are in the specifics of, we want to get a such and such kind of person right now.
Yeah, that makes sense.
And, it's sort of strange because we're a company where, we actually need things like history PhDs, because we actually do, stuff with, curating, all military conflicts in history type thing, where it's useful to, we need people. Actually, another thing interesting to mention in connection with Wolfram Language is if you look at the people who are, we have a whole lot of people who have, I would say, subject area backgrounds, and many of whom were not, quotes, computer people particularly before, but they're very smart people, and they, it's turned out many of them have become really, really strong Wolfram Language programmers, which is an interesting thing to watch. I mean, it's interesting to see that we see, in educational level, for example, like in K through 12 education, it's like, well, okay, which teachers are really going to understand this stuff? Is it going to be the math teacher? Is it going to be the computer science teacher who knows Java, for example? Or is it going to be the head of the English department who's just, a smart person who decides that they're going to pick the stuff up? Turns out, it's not. It turns out it's a diverse background of people, and that's the same thing we see in people who end up being, really strong Wolfram Language programmers. So I think I guess the point there is that it's whole world of kind of computational language and sort of computational thinking is the most important thing. It's a bit of a disruption relative to the we're all going to learn to be the best, churn out the maximum number of lines of code and make sure the type checking works correctly type thing.
Right. Yeah, that makes sense.
And, I think in anyway, that's some. So
that totally makes sense. I think the camp sounds awesome, especially for if people are interested in. As you said, maybe they have a great background in history or particle physics or something like that. And this is a great way to jump into computation and programming and things like that.
Right. No, it's been. I mean, look, the one for grown-ups, that's the case. The one for high school kids, that's interesting because it turns out that even at the fancy high schools, and we've tried very hard to get kids also not from the fancy high schools, but turns out that many fewer people are learning any kind of real programming, any kind of anything computational in high school than you might think. I mean, I'd kind of assumed with all the noise that's made about, everybody's, doing
everyone's STEM crazy.
Right. But it turns out a lot of these kids, and actually it's often the worst case is they did a C++ class and they found it boring and they learnt a bunch of, the most important thing to do is to, I don't even know.
Put a semicolon every time or something.
Yes. Right. It's anyway. Well, listen, I should be off, but
yeah, totally. So yeah, just to recap real quick. So if you're a student, you have access to Mathematica already. You might have not known it. So definitely check it out. I mean, it's totally free. Go through your university and start playing with it and see how many people there are in each country and do all these cool things. If you aren't a student, I believe, correct me if I'm wrong, but you can still use it for free.
Yeah, in fact, the web version, you can just go to the front of our website and it says immediate access and start up Wolfram Programming Lab, which is Wolfram Programming Lab is the full Wolfram language, but it's kind of themed for kids. Okay. So if you don't mind that it's themed for kids, you get it for free.
Cool. Good to know. And if you want to integrate it with something you already have half written, you can use the Wolfram language, which is also free, right, for personal use.
Yeah, I mean the Wolfram engine. I mean, this is where it's everything gets complicated at this point, but
sure,
basically it's been go to our website and you should find a path for
you can find good documentation. There's definitely at least a web way to sort of like a sandbox where you could play around and understand the language and everything.
And
cool. Thank you so much for coming on the show. This has been amazing. It has gone a little long, but I'm sure the people are going to be they're not going to be upset about that. This is an absolutely fantastic interview, and thanks for staying up late with us.
Sounds great. It was fun.
The intro music is AXO by Binar Pilot. Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix, adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.